All right, let's just jump right into this special explainer, where we are going to completely take the intimidation out of indefinite integration and, well, build your ultimate toolkit. If you've ever stared at a totally complex math problem and felt just completely lost, yeah, you're absolutely not alone. Integration can kind of feel like this tangled web of endless rules. But today, we're changing that. We are going to strip away all the confusion, focus purely on summarizing the core formulas and the manipulation tricks that actually matter, and hand you the master keys to unlock even the most brutal advanced equations out there. Think of this explainer as your complete definitive cheat sheet. So here is our roadmap for today. First, the foundation, then the art of simplification, tactical substitutions, advanced biparts, and finally, cracking the chakra view.
Okay, part one, the foundation. So think about it like this. Integration is literally just the reverse process of differentiation. Seriously, if you know one, you fundamentally know the other. When you need the integral of cosine, you just gotta ask yourself, wait, what function when differentiated actually gives me cosine? And boom, the answer is sine. Viewing integration as the antiderivative, that is the essential mental shift you need to make to stop just aimlessly memorizing things and start logically understanding them. But to truly build out our toolkit, we need to quickly look at the broader families of formulas, right? For polynomials, the logic reverses perfectly. Instead of dropping the power down like you do in differentiation, you increase the power by 1 and then divide by it. Simple. For exponential functions, specifically e to the power of x, they remain wonderfully unbreakable. The integral is exactly the same, e to the power of x. And for logarithmic outcomes, when you see a standalone 1 over x, that integrates flawlessly into the natural log of the absolute value of x. Summarizing these main families gives us a really robust starting point for tackling the harder stuff. Now, once you actually know those standard foundational formulas, you can instantly upgrade them. The absolute golden rule here is this: when substituting a linear function, never ever forget to divide your final answer by the coefficient of x. I really want to emphasize that you must divide by it. For example, if you know the integral of sine of x is negative cosine of x, then the integral of sine of 2x plus 3 is simply negative cosine of 2x plus 3, but then divided by 2. Forgetting that coefficient is literally the #1 trap students fall into. This single division rule is a rapid shortcut that just instantly expands your standard toolkit.
All right, let's move on to part 2, the art of simplification. Remove the power. Seriously, when you encounter trigonometric functions trapped inside powers, like sine squared or cosine squared, your immediate knee-jerk reflex must be to remove that power using double angle identities. Why? Because powers trap our variables. They break linearity, which stops integration dead in its tracks. We absolutely have to flatten them out. Just look at how dropping that exponent instantly changes the game. It transforms a total dead end into a perfectly manageable direct formula application. Sine squared x is a trap, but using the identity, it becomes 1 minus cosine of 2x all divided by 2. Now, just walk through this with me. We split this into two parts, a simple constant of 1/2 and a basic cosine of 2x. If we map this perfectly back to the foundational toolkit we just went over, the 1/2 becomes x over 2, and the cosine of 2x integrates to sine of 2x, and then we divide by that coefficient of 2. It is honestly like waving a magic wand over the problem.
Here is another brilliant little trick, forcing the denominator to appear in the numerator simply by adding and subtracting the exact same constant. This one takes a tiny bit of patience, so let's break down the 3 steps. Step 1. Look strictly at your denominator. Let's say it is x squared plus 1, but your numerator just has a lonely x squared. Well, step 2, just add 1 and subtract 1 on the top. You haven't actually changed the mathematical value of the equation, right? Then step 3, split it up. You now have x squared plus 1 over x squared plus 1, which beautifully cancels down to just a 1, minus 1 over x squared plus 1, which is your standard inverse tangent. It is all about purposefully manufacturing exactly what you need to break the equation apart.
Let's keep the momentum going with part 3, tactical substitutions and hacks. Welcome to a legendary little trick that a lot of students affectionately call couture putor. It's a fun, quirky name for a seriously powerful manipulation technique, making really smart adjustments by yanking out the highest power from the bottom of an equation. When you have this massive, intimidating algebraic fraction that looks completely unsolvable, pulling out the largest power of x from the denominator essentially forces negative powers to appear inside the brackets. So the real secret here is that when you differentiate a negative power, you actually increase the denominator's power, building exactly what you need upstairs. Think of it like a physical seesaw.
pushing the power down into the denominator creates exactly what we need to balance the equation upstairs. If you force a 1 over x to the fourth into the denominator, taking its derivative mathematically requires you to drop the power further, which gives you a negative 4 over x to the fifth. And guess what? This perfectly matches the stray variables floating in your numerator, allowing for a flawless, clean substitution that balances the entire scale. Now, for problems known as algebraic twins, there is a very specific 4-step protocol of dividing by x squared that unlocks a clean substitution path every single time. Let me just hand you the secret recipe for breaking down this brick wall. Step 1, identify the twin format, like x squared plus or minus 1 floating over x to the power of 4 plus 1. When you see it, don't panic. Step 2, divide everything top and bottom by x squared. Step 3, rewrap the newly formed denominator as a perfect square of x plus or minus 1 over x. And finally, step 4, substitute that exact group term as t. By strictly following this protocol, you turn an impossible, unintegrable wall into a wide-open door.
All right, part 4, advanced by parts hacks. So we always choose our first function based on the ILATE rule, prioritizing functions whose derivatives will simplify the overall equation. Now, you might be wondering, what on earth is ILATE? Let me decode that for you. It stands for inverse trigonometric, logarithmic, algebraic, trigonometric, and exponential. Basically, think of this as a literal priority line in a factory. You scan your equation, and whichever function appears highest on this list, say a logarithmic function over an algebraic one, gets chosen as your first function to be differentiated. The goal? You want to pick a first function that naturally degrades and gets simpler when you differentiate it, while pushing the functions that are really robust and easy to integrate, like exponentials, straight into the second position. But here is a highly advanced maneuver I just have to share with you. If you spot 2 linked integrals, here is the absolute secret. Do not solve both of them. Just hold one, expand the other, and watch the complex terms beautifully cancel each other out. Seriously, sometimes expanding one complicated integral using biparts naturally produces a negative mirror image version of the second integral sitting right next to it. By doing exactly half the work and leaving that second part alone, the equation essentially just solves itself. And that brings us to our final section, part 5, cracking the Chukar view. So a Chukar view is an ancient mythological labyrinth designed to trap you with overlapping, totally inescapable defensive layers. And honestly, that is exactly what a JEE advanced previous year question filled with fractional powers and massive polynomials looks like. Looking at it can feel like entering a maze you are never going to escape. But remember, it's just an illusion hiding a basic formula. The examiners specifically designed these to make you panic, but we know better. By simply applying our couture-pateur technique and pulling out that maximum power, the whole illusion shatters, leaving you with a straightforward substitution. Let's dig into the exact mechanics of how this monster is actually defeated. Imagine you have a terrifying polynomial trapped inside a bracket and it's raised to a fractional root, like the power of 1/4. The trick is to reach inside that bracket and forcefully pull out x to the 4th power. When that x to the 4th crosses the boundary of the 1/4 root, it mathematically simplifies. The powers multiply, 4 times 1/4, and it emerges on the outside as a clean single x. That single x then multiplies with whatever's already sitting down in the denominator, which often creates an x to the 5th power. Suddenly, inside the bracket, you have manufactured 1 over x cubed terms, and outside, you've got the exact derivative you need. You see the mechanics at play here? By yanking out the highest power, the terrifying fractional root collapses, negative powers are generated, and what looked like a multi-tier maze becomes a basic t substitution that you can execute flawlessly. Now, here is a really fascinating dilemma that popped up in another advanced paper. Can we use a trigonometric substitution on a purely algebraic fraction where it seemingly just doesn't belong? Usually, we're strictly taught to only use tan theta when we see a 1 plus x squared format. But what if we don't? Well, yes, you absolutely can. Substituting x equals tan theta in a non-standard algebraic setup is a wildly unorthodox, yet highly effective master key. By intentionally throwing tan theta into a complex polynomial, you force everything to convert into sine and cosine over tangent. By turning that master key, those messy, impossible algebraic gears lock perfectly into predictable trigonometric identities. Things cancel out, terms flatten down, and suddenly, you are right back in section 1, just integrating a basic trig function. And this brilliantly illustrates exactly why we learn these tricks, because this single unorthodox substitution was worth a massive 5 marks in a JEE advanced exam. 5 marks! That is literally the difference between getting stuck and getting ahead. The students who rigidly followed the textbook, they got trapped in the labyrinth. But the ones who understood the fluid nature of these manipulation tricks unlocked the answer and grabbed those points for sure.
So, you are now equipped with the foundational formulas, the simplification tricks, and the advanced substitution tactics, all the master keys. So, what complex problem are you going to conquer next? Remember, indefinite integration isn't about memorizing 1,000 different isolated scenarios. It's about knowing these core manipulation tricks, understanding how they dismantle the mechanics of the problem, and honestly, just having the courage to apply them. Keep practicing these adjustments, and I promise you, no equation will look intimidating ever again. Until next time, keep exploring.